My name is Hemant Chaurasia. Good afternoon, everyone. I'm a postgraduate student at Monash University in the Fluids Laboratory for Aeronautical and Industrial Research. Today I want to discuss with you my project, Instabilities in Flows over Bluff Plates. My presentation will begin with a background and motivation to the work. I'll then describe my project in an overview, methodology and results, and we'll finish with conclusions and opportunity for questions. Here, a submarine cruising through the ocean. And I put this here to illustrate the difference between the two main types of fluid flow. If we draw a line there, you can see that in front of the line, the water flow is smooth, whereas behind the line, the flow becomes rough and churning, chaotic. These are two distinct types of flow called laminar and turbulent. You may have heard of these before. And these have important consequences for engineering design. For example, turbulent flow will cause a different amount of drag on the hull of the submarine compared to the laminar flow. But what's interesting to me as a researcher is that we don't know a whole lot about how this laminar flow becomes a turbulent flow. This is not very well understood, and as a consequence, our ability to predict turbulent fluid flow is not very good. This is what my project is all about, understanding how turbulent fluid flow arises. What do I mean by Bluff Plate? Here's an everyday example from a very expensive place. Oh, there we go. There we go. That's a Bluff Plate. I've studied a geometry which is thin, long, wide, and it has sharp rectangular leading edges. In an animation, this is what my vortex shedding state looks like. You can see the vortices forming behind the leading edge of the plate, and then they move downstream. In my three-dimensional simulations, remember these were to check the results of the earlier work. I've got the plate in red, and the green surface shows you the positions of the vortices. You can see the same behavior as we expect, that the vortices form and they become deformed. Different view now. We can overlay that streamwise vorticity, that twisting measurement, in light blue and dark blue, and you see the same pattern emerging. So given that this is a sort of an independent check of the results, this confirms our finding that the elliptical instability flow pattern is definitely the key player causing turbulence from the beginning. So in conclusion, today I've shown you that prediction of turbulent fluid flow is important to a wide range of technologies, and that CFD simulations offer a cheap, fast, and versatile solution to this problem, with challenges still to overcome. I've shown you my research work in this area, and my finding that there is an elliptical instability flow pattern which could give us a much better handle on predicting turbulent fluid flow. And with this knowledge, engineering designers can come up with better ways to predict turbulent fluid flow, and this will have flow-on benefits for engineering designs such as better efficiency, higher performance, and new frontiers of technology, such as perhaps the next generation space shuttle.